Hello, welcome again. We are solving some questions of fluid mechanics and machinery. The topic is boundary layer flow. Question number 30 to 35 carries a common statement. The statement is for the velocity profile for laminar boundary layer u by small u by capital U naught is equal to 2 y by delta minus 2 y by delta cube plus y by delta 4. Uh, Question number 30, the momentum thickness is, these are the options. The shear stress at the wall is, these are the options. Boundary layer thickness in terms of Reynolds number is, these are the options. Um, Question number 36, the shear stress at the wall in terms of Reynolds number is, these are the options. Drag force is given by, these are the options. 35 is coefficient of drag in terms of Reynolds number is, these are the options. So momentum thickness, we know that theta is equal to u by u infinity 1 minus u by u infinity dy, and limits are 0 to delta. So u by u infinity is just 2y by delta minus 2y by delta cube plus y by delta 4. So putting these values of u by u infinity, we get this equation. Okay, so that is 2u by so 2y by delta minus 2y by delta cube plus y by delta 4. Okay, and this will be 1 minus 2y by delta plus 2y cube by delta minus y by delta 4 dy. Okay, so solving this and integrating this, we can get. So this is a slightly difficult calculation, and you guys can manage. Okay, so solving this and integrating this and putting a limit delta to 0, we get 37.37 by 315 delta. Theta is 37 by 315 delta. That is the momentum difference. Just we have multiplied by 1 and then by this equation, and then find out the theta is 37 by 315 delta. So second question is shear stress at wall. So shear stress at wall is given by tau is equal to mu curly u by curly y naught, and u is given as u infinity 2y by delta minus 2y square by delta 6 plus y 4 by delta 4. So du by dy will be this constant. Okay, now if we put y is equal to 0 here, then it will be dy y naught. Okay, so it will be 2 u infinity delta. So shear stress will be your 2 mu u infinity by delta. Okay, so that is your shear stress at wall. And next question is boundary layer thickness in terms of Reynolds number. So from the von Karman equation, we have tau naught is equal to tau naught by rho u infinity square is equal to curly theta by curly x, and theta we have found out, that is 37 by 315 delta. So curly theta by curly x will be 37 by 315 curly delta by curly x, differentiating with respect to x, and tau naught is this quantity 2 mu u infinity by delta. Okay, so if we can multiply, we can cross multiply delta x here and curly delta here. So it will be 630 by 37 rho u infinity mu x plus c, and delta square by 2. So if x is 0, delta is 0. If x is 0, delta is 0. That is the leading edge of the plate, and c is also 0. So c will be 0. Okay. So delta square by 2 will be 630 by 37 mu x by rho infinity. So delta will be your multiplying by x and dividing by x. It will be so to convert it into the Reynolds number. So delta will be 5.84 x by rex, because rho u x by mu is your Reynolds number. Okay. So next is shear stress in terms of Reynolds number. Next question is shear stress in terms of Reynolds number. So now we have delta in terms of Reynolds number, and we have shear stress in terms of delta. That is this quantity. So put in the value of delta, we can find out the shear stress in terms of the roll number. So that is 2u infinity mu by delta. Delta is 5.84 x root rex. So it will be 0.34 u infinity mu by x root rex. Okay. So that is the shear stress in terms of the roll number. Okay, and next is your drag force. So drag force can be found by multiplying by taking a small strip and multiplying it by a tau naught, because tau naught is the stress at the at y is equal to 0 or on the plate. So if we take a strip of thickness dx on the plate and multiply it by b, so that will be the shear area, and if it integrated up to whole length, then it will be drag force. So tau naught will be this quantity. Okay, so tau naught will be this quantity that we have derived, and it will converting rex into rho mu x, rho ux by mu, so that we can get terms in terms of x. And now it will be this quantity, constant quantity, and it will be x minus 1 by 2. So it will be x 1 by 2 by 1 by 2 and L to 0. So it will be your 0.68 mu u infinity root rho ul by mu. So that is drag force. Okay, and next is drag coefficient. So drag coefficient is nothing but fd by half rho a u into distance, and a is your b into l, area of the plate, and u infinity is free similar to fd is this quantity. So coefficient of drag comes out as, putting these values, we get coefficient of drag as 1.36 1 by root rho ul by mu, or 1.36 divided by root REL. Okay.